Hello and welcome to Machine Learning with Python 0 to GBMs. This is an online certification course being offered by Jovian. Today we're on lesson 5, Gradient Boosting Machines or GBMs. So let's get started. The first thing we'll do is go to the course page 0togbms.com. On the course page, you will be able to find a description of the course topics and you'll find lessons and assignments that you can complete to work through the course and earn a certificate of completion. Let us scroll down to lesson 5, Gradient Boosting with XGBoost. We will also talk about the course project today, where you will build a real-world machine learning model from scratch. But first, let's open lesson 5. On the lesson page, you will find a recording of this tutorial and some information about the lesson. And here is the notebook that we're going to look at today. The topic for today is gradient boosting machines with XGBoost. So I'm just going to click run here and select run on Colab. And this will take the Jupyter notebook that we were looking at on the lesson page and add it into your Google Drive. So you may have to authorize your Google Drive account and open it up in Google Colab, an online platform for executing Jupyter notebooks using Google's cloud compute. And Google Colab is free of cost, but if you wish, you can also pay for additional resources by signing up to Colab Pro. And if you have Colab Pro, I would recommend going to the runtime menu, clicking change runtime type and changing the runtime shape to high RAM, as the dataset we're using today is slightly large. Next, I am going to go to edit and run clear all outputs. This is going to clear all the previous outputs from the previous execution of the notebook. Now in the Colab notebook, I'm going to run the first cell, which sets up the integration between Colab and Jovian so that when we run jovian.commit, versions can get recorded properly and saved back to your Jovian profile. And once we run this, we will get connected to a runtime and we should be ready to go. So the topic for today is gradient boosting machines or GBMs with XGBoost. And there is another very similar library called LightGBM, which you should also check out once you complete this tutorial. And here's what we're going to cover today. We're going to download a real-world dataset from a Kaggle competition. We are going to perform feature engineering and prepare the dataset for training. We're going to train and interpret a gradient boosting model using the XGBoost library. We're going to train with k-fold cross-validation. So it's a different kind of validation technique. And we will also ensemble the results once we do the k-fold cross-validation. We'll also look at how to configure the gradient boosting model and how to tune its hyperparameters. Gradient boosting is a very powerful technique. It's probably one of the most powerful classical machine learning algorithms. So pretty much any problem concerning with tabular data, you may find it useful to try out gradient boosting. And it's based on a very simple but elegant idea, which we will discuss as we come to the model training. So let's begin by installing the required libraries. Now here I'm installing NumPy, Pandas, Matplotlib, Seaborn, Jovian, Open Datasets, XGBoost. This is the library we're using today, and GraphViz. This is required to visualize the trees that are created within XGBoost. And LightGBM as well, if you want to use LightGBM. And one issue you may face from time to time is when a certain notebook runs on your computer but does not run on Colab, or if it runs on Colab but does not run on your computer. Whenever you face such issues where the same code does not run in two different environments or maybe leads to an error in two different environments, you want to make sure that the version of the libraries that you have installed in the two environments are the same. So what I mean by that is if you do pip list and run it, you should be able to see the versions of all the libraries you have installed. And there is another tool called grep. So you can, after pip list, you can just type this pipe character, type grep, and let's say type XGBoost. And that will just show you the version of XGBoost that you have installed, which in this case is 1.4.2. If you do not have this grep, it's just going to show you a whole bunch of libraries, all of the libraries that you have installed, which may become too much. So that's why it's useful, especially on Colab, to just add a grep here and check the version. Now there are other ways to check versions too, but this is one that is standard across all packages installed because it uses the pip package manager. So we are using XGBoost 1.4.2. Okay, so we are going to take a practical and coding focused approach here. So we will learn gradient boosting by applying it to a real world data set. And we are going to pick the data set from a Kaggle competition. This Kaggle competition is called the Rossmann Store Sales Competition. And here is some description about it. Rossmann is a company that operates over 3,000 drugstores in 7 European countries. This is a real company and this is all real data. And currently Rossmann store managers are tasked with predicting their daily sales for up to 6 weeks in advance. Now, store sales are influenced by many factors. For example, if there is a promotion running at the store, or if the entire company is running a promotion, if there is a competing store nearby, the school and state holidays, because that affects people's behavior, seasonality, and locality. Now, with thousands of individual managers predicting sales based on their unique circumstances, the accuracy of the results can be quite varied. So you are provided the historical data for 1,115 Rossmann stores. And the task is to forecast the sales column for the test set. And your task is to forecast the sales column for the test set. So we will just look at the training set and the test set, but this is what we want to predict. We have data of 1,115 stores and we want to predict the sales on every single day. Okay. And we are going to download the data from this Kaggle competition. Now we just go to the data tab and this is where we can see some description about the data. So it turns out that there are 4 files: train.csv, test.csv, sample submission CSV, and store.csv. And we can look at the files here. So if you're unable to see this table here, just go to rules and click I accept the rules. Otherwise you will not be able to see the data. And here in the data tab, you can see train.csv. So train.csv, the file contains 9 columns. It's shown in a tabular format where you have some kind of a store ID. Store IDs go from 1 to 1,115. You have a date. This is the date. And they've conveniently also provided which day of the week it is, 1 to 7, Monday to Sunday, I would imagine. Then they have given you the sales in dollars on that particular date. They've also given you the number of customers who came to the store on that particular date. They've mentioned whether the store is open, whether the store is running a promotion, whether it was a state holiday, and whether it was a school holiday. So all of this is important information that can determine the sales. And let's check the test.csv file and let's see what's different here. So the test.csv file also contains stores 1 to 1,115. Apart from that, there seems also for each row, they seem to have added an ID. Presumably this is for evaluation of your submissions because you have to make predictions on the test set and submit it to this Kaggle competition. Then you have the day of the week and date as before. One thing you will notice is that the dates in the test set occur after the training set. And that's just to reflect how the model will be used in real life. You train on data from the past and you make predictions on data from the future. And then it has open, promo, state holiday, and school holiday. The things that it does not have is the number of customers and the sales. Now, this means that you cannot use customers as the input to predict sales, but you can use all the other things. You can use things like the store, the day of the week. Date, you will have to figure out what to do with it because all these dates occur in the future. So they don't exactly occur on the training set. Maybe we'll have to modify in some way, but you can use all of these things too. So this is a typical machine learning problem. You have a training file, you have a test file, but you have one more other file here, store.csv, and this contains metadata about the 1,115 stores. Now, if I go back to train, you can see that we have several rows of data for every store. it's not that if you check the total number of rows, you will see that the total number of rows is about 1.2 million. So for every store, we have data for the entire date range, which is from 1st January 2013 to 31st July 2015. On the other hand, if you check stores, we simply have 1115 rows, and we have some metadata for each store. We have information like the store type. We have information like the assortment. So this conveys something about what the store offers. We have information about competition distance. So I think this is how far away a competitor is, a nearby competitor is. Yeah, and you can check the description here. You have something called competition distance, which is distance in meters to the nearest competitor store. Then we have this competition open since month and open since year. So competition open since month gives you the approximate year and month of the time the nearest competitor was opened. Yep. So for example, this competitor is open since 2008, and September of 2008 was when this competitor opened. Then there is also this second promotion that is running here. So this second promotion, promo, indicates whether a store was, promo indicates whether a store was running a promo on that day. This is part of the training set. But there is promo 2, and promo 2 is a part of the store.csv file. So promo 2 is a company-wide promotion. It is a continuing and consecutive promotion for some stores. So if stores participate in this company-wide promotion, promo 2 has the value 0. Otherwise, promo 2 has the value 1. And this is not dependent on the date. This is just a store-wise configuration. And then there are a couple of other columns called promo 2 since week and promo 2 since year. So this means stores start participating in this company-wide promotion from a certain date and year. So you're given the year and you're giving the week number in the year when a particular store started participating in this company-wide promotion. There also seems to be another thing called promo interval, which describes the consecutive intervals promo 2 started. So it seems like with promo 2, you start this promotion several times in a year. Let's say maybe this is some kind of a competition that you're running or some kind of a raffle or something. So it seems like there is a certain promotion that you're starting multiple times. So promotion is started anew. And here, when you have Feb, May, August, and November, this means that each round of this promotion 2, this company-wide promotion, is executed by that store in February, May, August, November. Okay. So there's a lot of information here. This is something that you would have to read carefully and try to understand. But this is store-wide information, and we will have to figure out how to use this information on a day-to-day, in the day-to-day data, which is a train.csv data. Okay. So that's a quick overview of the data set. And finally, what we need to do here is make this file submission.csv file, and the submission.csv file should have IDs, and this ID should reflect the ID from the test set, and the sales here should be filled in with the predicted sales that your model comes up with after training on the training data for the test set. Okay. So the ID would be the ID from the test set like this, and the predicted sale would come here. And then you create a submission.csv file, and then you can make these submissions. So you given some training data, you have to train a model using the training data, and then you have to make some predictions on the test data, and then you submit these predictions. And once you submit these predictions on the leaderboard, you will be able to see where your predictions rank. Okay. Now this competition has already ended, but you can still make submissions and you can still track where you land on the leaderboard. Okay. So that's the data set, and we can download the data set from Kaggle directly within Jupyter using the Open Datasets library. Now, one option is to download this data from this tab here onto your computer and upload it to Colab. But the easier way is to just use the Open Datasets library and make sure to accept the competition rules before you try to download the data. So just go to the data tab, go to the rules tab and click I accept the competition rules and review them as well. Now, once you have done that, then we are just going to import Open Datasets as OD. And then I'm going to run od.download. And to od.download, we simply give the link of the competition, which is just this part, kaggle.com/c/Rossmann store sales. Now we give the link of the competition here, and you are then asked for your Kaggle username. And then you will also have to supply your Kaggle API key, which you can get by going into your account on Kaggle. So just click your avatar, click on account, and go down and click create new API token. And that's going to save the file kaggle.json to your computer. And once I open it up, I will be able to see my Kaggle credentials here. So I'm just going to copy this. Now this is a secret, so you should not be entering it. Don't save it in a variable within a Jupyter notebook. Okay, let me try that again. All right, so let me open my Kaggle key, and here I have my username, and I'm entering my Kaggle API key, and that downloads a dataset for me. Okay, and you can verify that the dataset is downloaded here in the file browser. All right, so let's check the files that have been downloaded. So as expected, it is the exact same files: sample submission, train, test, and store.csv. The first thing we'll do is load them into pandas data frames. So I'm going to load train.csv into this data frame called RossDF or RossmanDF. I am going to load store, test, and submission data frames as well. And let's take a look at each of these. So this is RossmanDF, and this contains exactly the information that we saw earlier: store, the date, the day of week for that date, the sales on that date, customers, open, promo, state holiday, and school holiday. And there are over 1 million rows of data. So that's a lot of data to train on. Then we have the test data frame. Here we have an ID, store, date, day of week, open, promo, state holiday, and school holiday. As before, no customers and no sales. Then we have the submission data frame. This is the data frame we have to generate. These are IDs from the test.csv file, and this is where we need to put in our sales to generate our submission file. And finally, we have the store data frame, where for all the 1,115 stores, we have a bunch of information. Now, the first thing I would do in such a situation is to simply merge the information from store DF into train DF and test DF, because it would be a lot more useful if this information was part of this train or of RossDF. So along with all of this, if we also had the information like the assortment at the store, the category of the store, etc., etc. So that's what I'm going to do. I am going to merge. I'm going to call RossDF, which is the train.csv file, .merge, store DF, which is the information about the store. And we are going to do a left outer join, which means that we want to retain all the days of data from the training set. We don't want to miss any days. And for each day, we want to add the information for that appropriate store. So we're joining on the store column. And a similar join we are doing on the test set as well. So this is what the merge data frame looks like. Now you have the store, the day of the week, the date, the sales, the customers, whether it's a state holiday, etc. And then you have store type, assortment, competition, distance, etc., etc. Okay. And of course, these details will get repeated several times. Each time we have a row where the store number is 1, all of these details will get repeated. Okay. Now this is the point where we would do some exploratory data analysis, and this is something that I will leave as an exercise for you. So study the distribution of values in each column and study their relationship or their correlation with the target column sales. Okay. So with that, we have downloaded our data set, and I'm just going to save my work here. So on Google Colab, when you run jovian.commit to save a snapshot of your notebook, you will be asked for an API key. So just go to your Jovian profile, click on copy API key, come back and paste the API key here. So just open jovian.ai, and in the get started tab, you should see this button. And once you paste it here, this notebook is now saved and a snapshot of this notebook has been captured and saved to your Jovian profile. So this is a snapshot of the notebook on your profile that you can run anytime. Okay. And you can always access this by going back to jovian.ai and checking the notebooks tab. You can see here. All right, so let's talk about pre-processing and a new and very important topic, feature engineering. So let's take a look at the available columns and see if we can create any new columns or apply any useful transformations. Now, one thing I'm already seeing here is that we have a date column, and just the date value by itself may not be very useful because all the information from the date in the training set belongs to the past, but all the dates in the test set occur after the dates in the training set. But what may be more useful from the date is maybe extracting some parts out of the date, things like the year, the month, the day of the month, maybe because a lot of stores have monthly cycles, so they may have higher sales or lower sales towards the end or beginning of the month. People get their salaries at the beginning of the month, so they may spend more during the first couple of weeks. So the day of the month might be useful. The week of the year might also be useful, whether it is the first week of the year, a lot of people are making new purchases, or the last week of the year when it's a holiday season, versus maybe somewhere in between where it's not as busy. So date is something that we may want to first convert it into a date time object. Right now it is just object. And second, we may want to parse out information from the date. So that's what we are going to do. We are going to extract different parts of the date. And because we have to do this both on the training set and on the test set, and later we will also have to do it when we try to make predictions on single inputs. So this is where we are defining a split date function. So the split date function takes a data frame, and first it converts the date column into the date time column here using pd.toDateTime. Then it extracts out the year, the month, the day, and the week of the year. And now we can call split date on merge.tf and merge.test.tf, both of these. So merge.tf is simply the train.csv combined with the store.csv file, and merge.test.tf is simply the test.csv combined with the store.csv file. And now we have a merge data frame, as you can verify here. And in this merge data frame, you will now see these things: year, month, day, and week of year. Note that we already have day of week, so we don't need to extract that. So we already know whether it's a Monday, Tuesday, Wednesday, Thursday, Friday, or Saturday or Sunday. And this is essentially what feature engineering is. A model may not be able to make a lot of sense out of a string to 2015-0731, or even if you convert it to a number of some kind. But once you put it in this format, you are now helping your model. A model will be able to figure out a lot more, because now it can pick up monthly patterns. Now it can pick up patterns that happen through the month. So the daily patterns. Now it can pick up the weekly patterns over the year, and it can also pick up the pattern during the week. Okay. So all of these patterns can now be picked up from our model. So that was one useful thing to do. The next thing to notice is that there is this column called open. This tells you whether the store is open on a certain date. And if the store is not open on a certain date, it's quite likely that there will not be any sales. So let's maybe verify that. If we just check from merge.tf, just extract those rows where merge.tf.open is 0, which means where the store is closed, and check those sales on those dates and see what all different values sales takes on those dates. So it turns out that the only value in the cases where the store is closed is 0. So there are 172,000 rows of data out of the million where the store is closed, and on all those days, the sales are 0. And you can verify this. If you remove value counts, you'll see that all these sales are 0. And that's what we've done here just by putting in dot value counts as well. Okay. So now instead of trying to model this relationship using a machine learning model, it would be a lot easier to just hard code this in our predictions. I mean, our model has a limited capacity or a limited power, whatever kind of model we're training. And the fact that it has to figure out that when open is 0, then the sales are 0. That is just some additional work which we can save the model. We can do a very simple hard coding here. We can just hard code this relationship in our predictions so that whenever we are making any predictions on the test set, for example, we can simply set the sales to 0 if the store is closed. So that's what we can do for the test set. What do we do in the training set? So in the training set, I would argue that the best thing we can do right now is simply remove all these rows and just train a model which works on data for when the store is open. Okay. So we are only building this model for the days where the store is open, and that will make it easier for the model to learn some of these other relationships, which are not as easy to guess. So here's what we're doing. We say merge tf.open equals 1. This is going to select all the days where the store is open, and we select all those rows of data. And so now for all the stores, all the days when stores are open are selected here, and we're just creating a copy here so that we can make some modifications to this data frame without affecting the old data frame. Okay. So now we've removed from the training set all the days and all the days or all the entries where the particular store was, which that row was referring to. We are not going to remove any rows from the test set because remember, we have to actually generate predictions for all the rows in the test set. So we can't ignore any rows. We're just ignoring from training because we don't want to train on data when the store was closed. Okay, so let's get into a little more advanced feature engineering here. Now there is this competition open, or there is this competition open since month/year column. If I just check merge tf, you can see here there is a competition distance. This tells you what is the distance in meters to a competing store from maybe a different company, and competition open since. So this tells you when this store was opened. So this store opened in September of 2008. And what day are we looking at here? We are looking at 2015 7/31, right, for this particular store. Maybe let me pick a sample so that we can see some variety here. Okay. So let's see this one. For example, we are looking at the data for store number 925 on 2015 March 7. So it's March 7, 2015. And it turns out that there is a competing store at 470 meters away, and that store has been open since 2007 March. All right. Now we can pass this information into the model, which is when the store opened and which month the store opened in, the competing store. But something that will be a lot more useful for the model is if we can simply indicate whether there is a competing store, and if there is a competing store, for how long has it been open. Okay. And how do we quantify that? We can simply maybe count the number of months that the store has been open for. So for example, if you're looking at 2015 here, so 2015 minus 2007, that is about 8 years, and March 2007 to March 2015. So that's about exactly 8 years and 0 months. So this particular store has been open for 8 times 12, 96 months. So I would argue that instead of telling the model that the competition has been open since March of 2007, it would be a lot more useful for us to tell the model that the competing store has been open for 96 months. Okay, on the particular day for which we are trying to model this relationship, right? So this is what we're going to do for every day, or for every row. We are going to pick out the current day, and using the current day and using the information in the competition open since month and competition open since year, we are going to calculate a new column called competition open. And competition open is simply going to be the number of months that the competing store has been open. And the general idea here is the longer a competing store has been open, the more impact it will have on this store's sales, because that's just a hypothesis, and that's something we're going to try out. Okay, and you may have different ways of looking at this, but this is just one approach that we're just going to try out and see if it helps the model. So we're defining this comp months function which takes a data frame, and first it checks how many years the competition has been open since compared to the current year. Remember, we've already extracted out year. So we can do 2015 minus 2007. And then we also add to it how many additional months there are. So if the current date is July of 2015, the date in the particular row, and the competition has been open since March of 2007. So we go 2015 minus 2007 times 12. So that's 12 8s 96. And then we go July, which is actually stored as a number 7, minus March, which is 3. So 7 minus 3 is 4. So we had 4 more months. So this will say that the competition has been open for 100 months. And of course, we are doing that row by row for every row. Okay. Now, the only difficulty is sometimes it's possible that maybe a competing store opened in 2014 or in 2015. So we don't want to put in information about the future into any row. So if we don't want to put in, for example, if we have information about store number 1, we are looking at January 1st, 2013. At that point, there is no competing store. So at that point, we should probably just put in 0 for competition open, or maybe put in some other number like NA. So that's one thing to take care of, that we don't want to put information about the future into the past. So that's why there is this additional line, and I'll let you figure out how exactly this works. But this additional line simply replaces the negative values with 0. So wherever the competition open has a negative value, which means that there is no competing store yet, but it will open up sometime in the future, then there we replace it with 0. Okay. So after doing all of this, the result is this. So if I just pick out the competition related columns, you can see here we have, and I'm just picking a random sample here. We have, this is one row from the training set. So we have this date 2013 5/18. Then we have the distance of the competing store 250 meters. Then we have the competitions open since year and competition open since month. And we have here calculated how many months the competition has been open for. Okay. And this is far more useful for our model than this or this. Okay. And this has been calculated using the date, using the competition open since year and competition open since month. All right. And in the cases where there is no competing store nearby, the value is 0. In the cases where a competing store will open in the future, in that case also the value will be 0. I can't find a good example here, but yeah. So let's suppose the date here is 2013 and the competition open since is 2014. Then this value would also be 0. Okay. So that's just some feature engineering that people try and do to make information, to present information in a form that can be most useful for the model. All right. Now there is another set of columns, which is to do with promo 2. So if you recall, promo 2 is basically representing a company-wide promotion that stores participate in, and it's a recurring promotion. So if a store participates in promo 2, then you will see the number 1 here, otherwise you will see the number 0. And then there is a certain date at which every store has signed up for this company-wide promotion at different dates. So you can see those dates here. Once again, we have year and we have week. So using this, maybe we can just identify for how long this store has been running a certain promotion. So we can just compute how many months the store has been running a certain promotion for. And then this promotion is something that is kicked off multiple times every year. So that's where we have this promo interval. And here this tells you that this promotion 2 was kicked off at that store every Jan, April, July, and October since sometime in 2010. Okay. So one thing we can do is combine these two to just compute for how long the promo 2 has been running at a particular store. And the second thing we can do is we can identify if at the current date in the current month is a new promotion starting, right? So we can just check that as well. And that might be useful information, because this by itself is not something that we can pass into the model. But if we can use this information, combine it with the current month, compare it with the current month, and create a new column telling us whether a promotion is getting kicked off in the current month, that might be a more useful piece of information to the model. Okay, so that is what we're going to do here, and there are a couple of functions that perform this. So this I will leave as an exercise for you. This is primarily just some pandas data frame manipulations, and the end result of all of this, once this is done, so the end result of all of this is that we are going to add a promo to open column. This tells you months since promo 2 was open at the store, and we are going to add a is promo 2 month, which tells you if the promotion was started in the current month. And you can see that here we have this promo to open. This tells you number of months since the promotion started, and you can verify here you have 2014 week 40, which means somewhere towards the end of 2014, and here we are looking at March of 2015. So for about 5 months this promo has been running, and this promo runs in January, April, July and October, so that's why you see 0 here. But if you had the matching month, then you would see a 1 here. For example, here you can see that this date is February. So here we have February listed in the promo interval as well. So here we have a 1. Okay, so now we don't need this column because we have this column is promo to month, and now we don't need this column, these two columns, because we have this column promo to open. And putting the specific computations aside, the idea here is that we did a join, we took some store-wide information, and then we used that store-wide information in combination with the day-to-day or in combination with the present date for each column in the training, for each row in the training set in combination with the present date to compute this new column, which gave us richer information about the data. And this is probably 70 or 80% of machine learning, which is cleaning the data, getting the data into the right shape, combining different data sources, engineering new features based on insights like this, that maybe we should keep track of how long a competitor has been open, or maybe we should keep track of how long a promotion has been open, etc., etc. Okay, so this is not very easy to come up with. This is, I mean, I've just pulled it out of some of the best notebooks that I saw on the Kaggle competition, and these are certainly even the best features. So you may have to think about what other features you can create. And if you have any ideas, do post them in the chat as well. But this is what is feature engineering: combining multiple columns, combining data frames, and transforming things like breaking out date into things like year, month, etc. Okay. So with that, we have now completed most of our feature engineering work. So if you now check merge TF, we should have a lot more columns. We have about 25 columns, some competition related columns, some promo related columns, and some date related columns as well. Okay, so let's move on. Now, once we've done this feature engineering, once we've done this exploration, and again, there is sort of an interplay here. It's not that you do feature engineering once and you're done. You do the feature engineering, then you do some more EDA, and then using that EDA, maybe you do some more feature engineering. Maybe you reject some of the features you created. Maybe you combine some of the features to get new features till you start seeing some kind of a pattern or some kind of a correlation. And it's not that it's once done and finished. You train a model, and if you see that the model is not good enough, maybe you need to go back and do more feature engineering. So although we are following a linear process, that is not how it will be typically. And this problem that we are solving over the course of 3 hours is actually something that people have actually spent 2 to 3 months solving for the duration of the Kaggle competition, right? So there's a lot of back and forth, and nothing is ever just done or finished. But that said, moving on from feature engineering, let us now select the columns that we want to use for training. So here we are going to select, these are all the columns that we have now either picked up from the dataset or created. And out of these, let's see which ones we are going to use as inputs. The store should be an input. We can keep that because the store numbers in the training set and the test set are the same. We are making predictions for the same stores. If we wanted to create a model which could work on a new store which is not seen in the training set, then we cannot use the store number. So keep that in mind. But in this case, it's the same 1115 stores, so we can use the store number. Then we have day of week. That is going to be useful for sure. We have date. We can drop date because we have extracted all important parts out of it. We have sales. This is something that should be the target column. So that this is what we've put in the target call. We have number of customers. This is not something that we can use because this information is not available in the test set. And of course, when you deploy the model, you want to make predictions for the next 6 weeks. You will not have the number of customers. Now, one thing you could do is you could train maybe a number of customer prediction model, a model that predicts number of customers, and then use the prediction of that model as an input to prediction of this model, etc., etc. But let's not go there yet. Right now, we are simply going to drop number of customers as an input column. Open is again something that we're not using. We've already gathered information from it, which is to drop all the stores, which were all the days, all the rows of data where the particular store was not open. And we are training a model only for the days where the store is open. So open is a useless column. It just contains the values 1 now. Promo will be useful. Whether the store is running a promotion or not is going to have an impact on the sales. The state holiday, school holiday, both of these are useful. So we're going to keep those within the input columns as well. The store type, assortment, again, seems like a very useful thing. So we should keep them around. And by the way, these are categorical. And you can verify this by just looking at the unique values for these columns. The competition distance, yes, this is useful, how far away a competing store is. Competition open. Now remember, these two we have combined into competition open, which simply tells you how many months the competing store has been open for. So let's keep that. Then the date has been decomposed into day, month, and year. So we have those. Then we have a week of year. We have promo 2. Both of these are useful. Which week are we currently in, and whether the store participates in promo 2. For how long the store has been participating in promo 2. So this is the number of months. And if promo 2, a new round of promo 2 kicks off in the current month. So all of this is useful information that we'll keep. The things that we have now engineered away, we can remove, like date, open since month, open since year, promo 2 since week, etc. And the target is sales. So once again, I'm just going to get the input columns out here from the merge data frame and create this data frame called inputs. And I'm just going to get the target column out. So now it's a single column, and create a merge data, create a single series. So targets will be a series and inputs will be a data frame. And I'm also creating copies here because this is a very small data set. I don't have to worry too much about creating multiple copies. But if you're working with a really large data set, maybe you shouldn't create a copy and you just have to modify the original data. So you can now check, this is inputs. This contains just the input columns. And one thing that you should note here is there seems to be this seems to be a categorical column, state holiday, where it has not just 0 or 1, but there are several types of holidays that it tracks, A, B, C, and D. And then store type, assortment, these are also categorical columns with text. So I'm sure we'll have to handle them separately. And the rest of them look numeric, although one could argue that maybe we should treat day of week as categorical because sales generally are not linearly correlated with the day of the week, like Monday to Sunday, there isn't a linear increase. So we should probably treat them as categorical. One could argue the same for day, month, and year as well. But yeah, and this is where you will have to choose which of these do you want to treat numerically and which of these do you want to treat categorically. Now, the good thing again is if you're using decision trees can typically work with both types because decision trees can create these decisions like is day of the week less than 1? So to pick the day of the week 0 and the rest of the days of the week will go in another direction. So decision trees can actually pick out using binary decisions, the days like if Friday, Saturday, Monday are specific branches that decision trees can create, even if you don't create separate columns for each of these days. Okay. So yeah, but that's still a decision that you have to come up with. Should we treat some of these as categorical or some of these as numerical? So that's inputs, and let's take a look at targets as well. And that's targets here. So these are the things that we're trying to predict. This is the sales. And we're also going to generate test inputs simply from merge test tf. We're going to get the input columns and then create a copy. So now this will contain just all the test inputs. And at this point, hopefully, the test inputs and train inputs should have the same number of columns. If they don't, then obviously you are not going to be able to train a model which can make predictions on the test set. So when you get to this point where you've selected some input and a test column, input columns, make sure that the test inputs and train inputs have the same number of columns, which in this case is 16. Okay. Then here is the somewhat subjective exercise of picking the numeric and categorical columns. Now there are some binary columns which have 0, 1 values. We don't really need to one-hot encode them. They're already one-hot encoded as 0, 1. So I'm put them into numeric just to keep things simple, to avoid this one-hot encoding and introducing new columns. Now with some of these things like month and day, these could be made categorical, but I chose to just keep them numeric and see what happens. You can try and convert them into categorical columns if you want and see if that has an effect. So the only things that I'm keeping categorical right now are the day of the week, because there are only 7 of them. Whether it's a state holiday, so there are these values A, B, C, it's definitely not numeric. Store type and assortment, and both of these are also not numeric. Okay, so these, whatever are the textual columns, I am making them categorical, and specifically one exception I've made here is day of week. But you can try and experiment with this and see if you get a better result. Okay, so let's now impute the missing numerical data. And instead of doing an imputer, let's maybe just check where the missing numerical data is. So it turns out that the only place where numeric data is missing is competition distance. And this is possibly because for certain stores, there is no nearby competing store. So in such cases, and the same is true for the test inputs as well, and there are no other columns where there are any missing data. So let's think about this for a moment. We need to put in a number here for competition distance. Otherwise, some of our models may not train. And a missing value here for competition distance indicates that there is no competing store near this store. Now, if we put the value 0 here, or if we put a very small value here, then that would be the opposite. That would mean the opposite. That means the competition is right next door. So we should probably not put the value 0 here. What we might instead want to do is maybe just put a very large value here. Like if, let's say, just instead of saying that there is no competition nearby, let's say that there's a competition is 100 kilometers away or something like that. Just to sort of retain the meaning of the value that is inserted here. 0 would mean that the competition is next door. That's not what we want to suggest. We want to suggest that there is no competition nearby. The closest thing to that is to suggest that the competition is really far away. So here's the trick that I'm going to use. I am going to fill these empty values with the highest value for the competition distance column. So let's check max distance. So max distance is 75860. That means about 75 kilometers away. So that seems reasonable. 75 kilometers. Maybe if I want, I can even double that number and make that 150 kilometers away. So I'm just going to fill in that wherever competition distance has the value none or nan, I'm going to fill the value 75860 times 2. So I'm just going to say that the competition is 150 kilometers away, which basically has the same meaning as this store not having any competition. Okay. So this is again something that you will have to do very carefully. When you are filling in missing values, it's not simply a matter of just using an imputer and putting in the averages or putting in the means or medians. Sometimes you have to think about what it means to fill a certain value. To fill the mean would change the meaning, because then you would say that the competition is maybe like a few hundred meters away, but rather what we want to put in here is to say that competition is really far away or does not exist. Okay, so although we have seen these standard strategies for imputing values and scaling values, you will have to apply some thought to it when you apply it to real world problems. The standard strategies are fine. when you want to just quickly get to a machine learning model. But when you really want to improve the model, these are all things that you have to think carefully about. Okay, let's then scale numeric values. I don't see any problem here. I think we can just scale them all to the 0 to 1 range. That should be fine. So we are using a min-max scaler to do that. And then let's encode some categorical columns as well. Now note that for categorical columns, we've mostly picked out columns which have text data. So what will happen is we will take each of these unique categories and create a column for each of these categories and just put in the values 1 and 0, depending on whether the row contains the category for that column. Okay. So that's what we do using one-hot encoder. Again, imputation, scaling and encoding, one-hot encoding is something that we've covered probably 4 times now, and hopefully starting to sound boring and repetitive and routine essentially. So just go through the previous tutorials if you want to understand how these work. Now, one thing I want to point out is we have not created a validation set yet. And this is because we are going to use a different validation technique called k-fold cross validation. We'll see that in just a moment. But that's all the data preparation that we need to do. And I encourage you to look through notebooks created by participants in the Kaggle competition. You can look through notebooks by going to this link. This is basically the code tab of the competition, and on the code tab, just select most votes to sort by the most popular notebooks and just go through some of these notebooks and see what other kinds of feature engineering people have done. And even the visualization, exploratory analysis, etc. will help you learn a lot, because a lot of these people are professional data scientists and they're putting in the same amount of care and the same insights that they apply to their day-to-day work at their job into this competition. So there's a lot you can learn, and this kind of information is not available anywhere in any book or any course. In fact, this entire notebook has been created just by looking at a bunch of different notebooks from the code tab of this competition, right? So do check that out. Let's do a quick recap before we move forward, just to revise what we did for feature engineering. So we downloaded the dataset. We downloaded the dataset, and that gave us a training CSV file, a test CSV file, and a store.csv file with some metadata about stores. All right, so we have a training set, and then we have a test set. The test set contains about 40,000 rows of data. And then we have the store dataset, which we merged into the training and test sets. So that's one thing that you will have to do often, merge data from multiple sources or perform some kind of joins to augment the training data. Then we looked at the dates and we extracted information like the year, month, day, and week of year from the date. And that gave us a merged data frame with these additional columns. Then we looked at whether the store was open or closed and realized that when the store is closed, the sales are 0. And we decided that this is not something we want to model. This is something we will hard code into our predictions. So we removed all the rows where the store was closed and the sales were 0. Next, we added some columns for the competition. So instead of having the month and year since the competing store opened, we just have the number of months since the competing store opened, a single value, which will be more useful to the model. Similarly, we added a couple of columns, one called promo to open and is promo to month. Promo to open indicates for how long the store has been participating in promo to, a company-wide promotion, and promo to month to keep track of whether the current row has a month when the promotion starts at the current store. Then we identified the input and target columns, and then we created inputs and targets, 2 data frames. Then we identified the numeric and categorical columns as well. And then we imputed the numeric columns. And this time we had to take a specific decision to put in a very large value for competition distance. Then we scaled the numeric values to the 0 to 1 range and encoded the categorical columns, which were strategically chosen so that some of the categorical columns which have numbers, we've kept them as numeric columns, so we don't want to change them. And finally, we've put together these 2 variables, X, which contains our training plus validation set essentially. So which contains just the numeric data from the numeric columns and the encoded categorical columns, right? So that is what X is. It contains all the data that can be directly fed into a model. It is all numeric. It has no empty values. And similarly, we have X test, which is just all the inputs that will be used to make predictions for the test set. So that's our X and X text, and X and Y are commonly used to refer to inputs and targets in machine learning. That's why we're using uppercase X and uppercase X test. All right, so we're finally ready to start training our gradient boosting model. And here is how a GBM model works. A GBM is short for gradient boosting machine. So first, we're trying to predict the sale at every store. The first thing that the gradient boosting model does is to predict simply the average value of the target column, compute the average value of the target column, and use that as an initial prediction for every input. So the model completely ignores all the training data that it is given. It simply looks at the predictions or the target values, and it simply takes an average of the target values and it uses that as a prediction. Now, obviously that's not a good prediction. So whatever error function you're using, let's say mean squared error or whatever, the prediction is going to be pretty bad. But here is where it gets interesting. Now, once you have predicted, once you've made one set of predictions, which is the averages, then we go back into each row of training data and we calculate the difference of the predictions with the actual targets. So just to convey that, let's maybe work through an example here. Let's say we have three things. We have month. Let's say we have month, and then we have day of month, and we have competition distance. So let's call that CD, competition distance. And then we have store number here. And then we have the sale. Okay. So we have a bunch of stores. So there is some information here for this store. And then the sale here, let's say the sale was 700. Then there is some information for a second store at a second date. And let's say the sale on this, for this training row, the sale was 800, and we have another one. And let's say the sale here was 970, etc., etc. And like, let's say 850 here. So these are some rows from the training data. So the first prediction that our model is going to make is simply the average of these numbers, average of 700, 800, 900, and 850. I believe this would be, let's say this is around 820. So it just predicts 820 for all of them. Okay. So it just predicts 820 for all of them. Now that's a bad prediction. So let's call this P0 or prediction 0. Now using these P0, it is going to compute the residuals. Now what is the residual? It is simply the difference between the prediction and the actual sale. The sale, difference between the actual sale and the prediction. So in this case, the residual should be minus 80. Minus, not minus 80. The residual should be 700 minus 820, so minus 120. In this case, the residual should be 800 minus 20. 800 minus 20, that's minus 20. In this case, the residual is 970 minus 820, that is 150. And in this case, the residual is 850 minus 820. Excuse the poor handwriting. And that's 30, okay? So now this is what we know, that in our current set of predictions, we are off by this much for each row. So here is what happens next. Now the model takes this input. So it takes all these inputs, and instead of trying to predict the sale price, it builds a decision tree to predict this value. Okay. And then it takes this input, and using this input, it tries to predict this value, and so on. Okay. So a decision tree is created. So now we create a decision tree. Let's use this to just represent a decision tree, and it's not an unbounded decision tree. Typically this is bounded in terms of depth. So we create a decision tree, and using this decision tree, we now try to predict how much we were off by when we made the first prediction. So when we made the first prediction, we were off by 120. And now suppose our decision tree predicts here minus 80. It predicts here minus 30. It predicts here that we were off by 70, and it predicts here that we were off by 40. Okay, so this is what our first decision tree predicted. Now using the first decision tree, so now we have this decision tree. Let's just call this D. So this is the prediction of the decision tree, which was an attempt to predict the residual. But of course, this is itself not that perfect. So what do we do next? We compute the next set of residuals. So the next set of residuals would be, let me just write that here. So the next set of residuals would be, I wanted to predict minus 120, but I predicted 80. So I'm still off by minus 40. I wanted to predict minus 20, but I predicted minus 30. So that means I'm off by plus 10. I wanted to predict 150, but I predicted 70. So I'm off by 80, and I'm off by minus 10, right? So this way we continue, we keep getting residuals. So this is what this picture is representing here. First, we use the average, and that's obviously very bad. So the error is very high. Then we train a decision tree to compute the residuals or the errors that we incurred when we were predicting the average. So that is these errors. We trained a decision tree to do that. Once again, we don't do a perfect job, but it is better, right? If you see, if I simply add up the prediction from the original model, 820 plus minus 80. So the overall prediction from the model becomes the first prediction plus the prediction of the first decision tree. So 820 minus 80 becomes 740. So 740 is now a lot closer to 700. Similarly, 820 minus 30 is 790. So 790 is a lot closer to 800 than 820. Similarly, 820 plus the prediction of the first decision tree 70 is about 890. So 890 is a lot closer to 970 than 820 alone. So almost all the predictions now become better because we have trained a decision tree to compute the residuals. Okay. So as soon as we create one decision tree, all our predictions become better. And how do we make the predictions? We simply add the original prediction plus the prediction, the predicted residual by the decision tree. But of course, we're still not perfect. We still will not have a perfect model. So then we train another decision tree to compute the residuals that were obtained after taking the result of the original guess and the first decision tree. So that second decision tree is trying to correct the errors made by the second decision tree, made by the first decision tree, and that reduces the error further. Then we train another decision tree, and that attempts to correct the errors made by the third decision tree. Okay, so that's how gradient boosting works. And let's just go over this step by step and try to understand this again. So the average value of the target column is used as the initial prediction for every input. That's the starting point. Then we compute the residuals of the predictions with the targets. So we now identify how much we are off by, what the error in our prediction is. Then we create a limited depth, a decision tree of limited depth to just predict the residuals for each input. Now we're not trying to predict the entire sales, and in some sense it's a smaller, more contained problem, right? We're just trying to correct the errors of our initial guess. Then here is a step that is an additional step, which is called the learning rate. We take the predictions from the decision tree and then we scale them using a parameter called the learning rate. So we don't directly add the prediction of the decision tree to the original prediction. We just scale it a little bit, and I'll talk about that in a second. Then those scaled predictions from the decision tree are added to the previous predictions to obtain the new and improved predictions for that particular row. And then steps 2 to 5 are repeated to create new decision trees, each of which is trained to predict just the residuals from the previous prediction. Okay, so that's how a GBM works. And let me talk about scaling now. So coming back here, we had this data. So we had this input columns, and the target that we are trying to predict was, what was it? Target was 700. And we predicted the average. The average was 820. So this was our initial prediction, P0. Then we trained a decision tree, then we computed the residual. So let's call that R0, and the residual is minus 80. And then we do it for all of these columns. We compute the residual. Then we train a decision tree, D, and D is trying to predict these residuals. So D is trying to use the inputs to predict the residuals. And again, D is going to be off by a little bit. So what is the number we used here? Let's say that D predicted minus 40. Now what we do is we actually have a learning rate parameter, and this is called alpha. And let's say alpha is set to 0.5. So instead of predicting 820 plus minus 40 as the prediction from our model after creating one tree, we actually predict 820 plus alpha times, or 0.5 times minus 40, right, which is the prediction. So the actual prediction that we are now making, and this prediction is the prediction from the original average plus the alpha, the learning rate, times the prediction from the decision tree. So 820 plus alpha is 0.5 multiplied by 40. So minus 20, 820 plus minus 20, that is 800. Okay. So this is the prediction, and this prediction is coming from P1 comes from our average plus our first decision tree. Okay. That's how P1 comes in. Then once we have P1, we compute the residuals R1, which is how far away the first prediction is from the actual value that we're trying to predict. It is still off by minus 20. And then we compute that for all of them. Then we train a decision tree to use the inputs to compute this residual. So now we have D2, and let's say it predicts minus 10. Here, the residual, it's still not perfect because it's not a full decision tree. Then once again, we multiply this by alpha. So we go 0.5. So we go the initial average A plus alpha times the decision from decision tree 1 plus alpha times the decision from decision tree 2. So once again, we multiply this by 0.5. So that means now we get to 805 as our P2. And then we compare 805, and we're still far away from P0. We're still far away from the target. So then we compute the next residual, R2. So R2 becomes 5. And that's how it proceeds. Okay. So ultimately the prediction of the model P for a particular input is the average A plus alpha times the prediction of decision tree 1. And what was decision tree 1 trained on? It was trained to predict P minus A, essentially, the residual from the original average, plus alpha times decision tree 2. And what was decision tree 2 trained to do? The decision tree 2 was trained to predict the difference between this and the actual target that we have, right? And then we have alpha 3, and alpha 3 will have decision 3, and then so on. Okay. So you can configure alpha. This is called the learning rate, and you can configure the number of iterations or the number of decision trees that you create. And that is called the number of iterations or the number of estimators. Okay. And that's all it is. That's all a decision tree is. That's all a gradient boosting model is: successively improving our predictions by training these small decision trees to correct the errors of the model that we have so far. Now, why do we have this alpha in place? Why don't we simply add the predictions from the previously trained decision tree? So it turns out that alpha prevents overfitting. If we apply that scaling factor to the decision tree that was just trained to predict the residuals, so we are intentionally creating some error there, which can be then filled in by the next decision tree and so on. And that helps prevent overfitting to the training set. So that's one thing. And then second, why is this called gradient boosting? It is called boosting because boosting is the name of the general technique where you train a new model to correct the errors or to improve an existing model. So whenever you have this kind of a system, as opposed to bagging, which is what random forests do. Remember, with random forests, each decision tree tries to make the entire prediction. That is called bagging, bootstrapping, bagging, etc. But boosting means you are correcting or you're improving an existing model. So the second decision tree depends on how the first decision tree was created. The third decision tree depends on how the second decision tree was created and its predictions and so on. So that's boosting. Now, why is it called gradient boosting? Well, in some sense, this is similar to the gradient descent algorithm, and the objective here is to minimize the loss. So we have a certain loss like mean squared error or some kind of a loss function. And the objective is to create new decision trees to minimize that loss, right? So in some sense, we are doing iterative gradient descent. So that's the mathematical term for it. And that's why it's called gradient. So gradient boosting machine is simply a boosting technique which tries to minimize the error by creating new estimators or new decision trees each time. And that's what it is. Okay. So try and describe in your own words how a gradient boosting model machine differs from a random forest. And do check out, if you want to check out the mathematical explanation for this, do check that out as well. But I will warn you that when you look at the mathematical explanation, it is pretty hairy. There's a lot of equations. So unless you're comfortable with the math, I would not recommend it. And there are some graphs as well, but it doesn't really help. But yeah, do check it out if you're interested in checking it out. But really the most intuitive explanation that I found is just the fact that gradient boosting machines add more decision trees to correct the errors of the decisions we've made so far. Okay. I also like this tutorial series on this YouTube channel called StatQuest that you can check out. This is a 5-part series, I believe, gradient boosting. Yeah, there are 4 or 5 parts. This also gets into the mathematics, but this also has a bunch of visual explanations. So you can use that to get a good sense of it. But as long as you're getting the basic idea that we are training more trees to correct errors from our previous trees, you should be fine. We're always using all the input features. Now to train a GBM, we can use the XGB regressor class from XGBoost. There is also a gradient boosting machine in scikit-learn, but XGBoost is far more efficient and far more versatile. So from XGBoost, we're just going to import XGB regressor. And let's check out what that looks like. Here you can see all the parameters that it accepts. And you can now see that there is this number of estimators, which tells you how many trees you are going to create. And you can now experiment with this. You can try setting number of estimators to 1 and see how that changes. See how many trees get created and try changing it to 2, 3, 4 and see how many trees are created. And then there is this max depth. So you can configure how deep each tree goes. Why do we need a max depth? Well, think about it. Coming back here, if we trained an unbounded decision tree, then that unbounded decision tree would essentially exactly fit the residual. So it would completely overfit to the training set to predict the residual. And once again, that would be a problem. So all of these are regularizations, because if it overfits to the training set, then it's going to perform poorly on the validation set. So typically these trees are not very deep. Then you have this learning rate, and this learning rate is basically just the alpha, or it's called eta, I believe, in XGBoost. It is simply the factor that is applied, the scaling down, the damping factor that is applied to the residual prediction from each decision tree. Once again, this is used to avoid overfitting. Otherwise, you may overfit to the training data. And then you have a bunch of other parameters. So I am simply going to create an XGB regressor here, and once again setting some random state and end jobs. Random state is simply to ensure that the randomization is using this number 42 as a seed, so that each time we run model.fit or each time we run this piece of code, we get the same results. That's what random state is for. And if you change this number, you will get different results, but each time you will get the same result when you put the number 7, for example. Then you have end jobs. This is simply to configure the number of threads that it should use in the background. When you put in -1 here, it will use all the threads that are available on the machine that we're connected to. Then here is the number of estimators, or the number of decision trees that we will create. So we'll start with the average, train one decision tree to correct the errors, train a second decision tree to correct the errors of the first two combined, and so on. We'll create 20 decision trees, and each decision tree will have a maximum depth of 4. So let's call model.fit now. And this takes not too long to fit, because it's 20 decision trees, each with a maximum depth of 4, shouldn't take more than a few seconds. So it took about 8 seconds. And you can see some of the other parameters here as well. And you can look up the documentation to learn more. And right now I'm just fitting it on the entire training set. We will talk about validation shortly, but right now I've just fit it on the entire training data that we had, using the inputs X and the targets. And now here's an exercise for you. Can you now describe in your own words how a gradient boosting model fits this machine learning training workflow? We take some inputs, put them into the model. It makes a first guess, which is just the averages. We compute the loss, we compute the residuals, and then we train a decision tree to predict the residuals. Now we put in the inputs once again. Now we get the output as the average prediction plus the prediction of the decision tree scaled down. Then we compute the residuals again using the targets, and then we optimize by training another decision tree and so on. Okay. And we can now make predictions using the model. So right now, since we just have the training set, we've not created a validation set. So I'm just going to call model.predict X. And these are the predictions of the model. Okay. And then we can evaluate this just in the same way we've been evaluating all our models. So I'm going to use the root mean squared error. So I've just defined this RMSE function. We give it the predictions and we give it the targets. And it turns out that the training error or the loss on the error or the loss on the training set is 2377. Okay. And I just want to point out here, you can create a validation set if you want. It's not that gradient boosting will not work with validation sets. It's just that we are using a different strategy for validation. That's why I've not created a validation set yet. Okay. But there's no fundamental limitation in creating validation sets for gradient boosting. You can, and we will. So now we get a RMSE of 2377. And going back, if you just think about the average sales, let me just go merge tf dot sales dot min and max. I guess the min is 0 in a lot of cases, but so the maximum sales is around $41,000. The min is around, min is 0. And you can also look at the histogram. But if you're off by 2,300, I would say that's not too bad. You know what, maybe just let's also look at a histogram. Let's do plt.hist merged tf.sales. I'm just going to pick a sample of maybe 10,000 rows just to get a sense. Yeah. So this is what the distribution primarily looks like. It seems like most of the sales are around around $5,000 to $10,000, and seems like we are off by 2377, right? The RMSE is 2377. So that means our predictions are off by $2,300. And that's not too bad. It's not like our predictions are in the range 5,000 to 10,000 and we are off by a full 10,000, which means our predictions are completely meaningless. We're off by 2,000 or so, which is probably not that great, but it's not too bad as well. So already we can see that our gradient boosting model gives us a fairly good result. And what I would encourage you to do at this point is maybe compare it with a baseline model. Maybe just build a very dumb model which always maybe predicts the average or the average of the same store for the last month or something like that. And compare it with a linear regression model, compare it with a decision tree and a random forest, and see if gradient boosting is any better. And the reason it is better in a lot of cases is simply because of this residual trick, because each time for each tree, we are reducing what it needs to learn rather than random forest where each tree has to learn the entire relationship. Now, in this case, each tree just tries to fix the errors of the previous tree. So that's how you evaluate, make predictions and evaluate, just as you do with any other scikit-learn model. You can also visualize individual trees using the plot tree function from XGBoost. This also requires the GraphViz library to be installed, so you will have to install that. But here's what it looks like. We say plot tree, and then we pass in the model. And the model, of course, contains many trees. And then we pass in this num trees argument. And this num trees is improperly named. This should be called the tree number or something. So here you are just passing the tree that you want to plot. You want to plot tree number 0, the first decision tree that was created, or tree number 1, the second decision tree that was created, or so on. So let me just plot it, and I can plot it left to right, which is nice, convenient to look at. So here's the first decision tree that was created. Promo less than 0.5. That's what we're checking. So it seems like whether there's a promotion running or not seems to be the biggest factor. Then if there was no promotion running, then it depends on the day of the week. And again, with the day of the week, we're checking day of the week less than 0.5, which, day of the week 1, which means whether it was a Monday. So if it is not a Monday, then we check the month. If it is a Monday, then we check something else. So this is what the first decision tree looks like. And I will draw your attention to these values. You see here 23091823, and maybe you'll also see, yeah. So all of these are not predictions for the actual sales. This is simply the deviation from the average that we are predicting here. And if I show you the next tree, num trees equals 1, this is going to try and correct the issues that have been created by the first tree, or the residuals that remain after adding the first tree. So here are the leaf nodes, and you can see that these numbers are getting smaller. These are no longer that large. These are definitely smaller. And if I go to tree number 19, which is the final tree that we've trained, which is trying to correct the errors of the sum of all the first 18 trees and the average, you can see that here you have numbers like -19, -234, 3. So it's making very small adjustments, right? So even though these trees are all very small, each tree can correct the previous tree in a meaningful way and contribute to an improvement in the result. Okay. So now notice how the trees only compute residuals and not the actual target values. And we can also visualize these trees in a textual format. So if we just run model.getBooster, this is the underlying structure that XGBoost creates, and called .getDump. That gives us a list of trees, tree objects in text. And there are 20 trees, not surprisingly. And here is the first tree in textual format. So you can see how it makes its decisions. And just like decision trees in random forest, XGBoost also provides a way to understand how important each feature is. So the feature importance score. And you can look into how this is calculated, but there are a couple of ways. One is called the gain, which has to do with how much each feature has contributed to reduction in loss over all the trees. And second is called the weight, which counts how many times a particular feature was used to create a split. Okay. So one is the number of splits, which is called weight, how many times a particular feature was used to create a split across all the trees. And second is the gain, which is how much it has contributed to reduction in loss. So you can see reduction in loss is called gain, right? So that's how the word is derived. So here is the importance data frame. So we just pick model.feature importances, and we put that into a data frame where we're also putting the columns from the X, or the data we used to train the model. So here we have features, and here we have importance. And we can now plot that and see that as well. And this is what it looks like. As expected, promo has a big effect, and then store type seems to have a big effect too. Day of the week, whether it is 1, I'm guessing then maybe, I don't know if day of the week 1 represents Sunday or Monday, but that's something that I would check. But it seems like that has a big effect. Promo 2 seems to have an important effect as well. So it's good that we added a bunch of columns related to promo 2. Competition distance, as one might expect. Assortment, then month, store, and day. Interesting that adding month and adding the day may have significantly improved our model. So what I would encourage you to do at this point is maybe turn off some of the features and try to retrain the model and see if you still get a good enough result. And it's possible that you may, it's possible that you may not. So this is how you figure out if the features that you've created are working or not. You look at their importance, you look at the before and after, and you have to keep all of this information organized in some fashion in some sort of a spreadsheet where you note down each experiment you've tried and the result that you got for that experiment, and potentially also keep track of that specific version of the notebook so that you can replicate the experiment if required. Okay. Now notice that we didn't create a validation set before training our XGBoost model. This is because we want to use a different validation strategy this time. This is called k-fold cross validation. So in k-fold cross validation, we take our training data, which is separate from the test data. The test data is supposed to be used only at the very end, but we take our training data and we split that into many parts. So when you say k-fold, k can be configured. Let's say k is 5. So we split it into 5 folds or 5 parts. It's like taking a piece of paper and folding it 5 times. And then each time we train 5 different models, and for each model, we use a different fold as the validation set. So we take split 1 and we train a model on split 1. And here we use the first 20% as the validation set. For split 2, we use the second 20% as the validation set. For split 3, we use the third 20% as validation set, and so on. And we use that for hyperparameter tuning. We use that for just experimenting between different modeling strategies. And the benefit of this is that we are not sacrificing on any of the data. For training, we are using all the data for training, but at the same time, we still have a way to analyze how these models are doing by looking at the validation score for each of the splits. Okay. So that's what we'll implement, and k-fold is quite useful for small data sets. It's not very useful for the really large data sets like this one, where we have millions of rows, a million rows actually. And the other thing to keep in mind also is that k-fold may not be the optimal strategy here, because our validation set should ideally reflect what kind of data the model will see in real life. It should ideally be closer to the test set, and the test set occurs in the future after the training set. So ideally the validation set should be in the future of the training set. So we are breaking that. Requirement here. So potentially the validation score that we get will not be as useful as we might get if we simply use the last one, right? So those are some things to consider, and we are doing it here primarily to demonstrate how to use k-fold cross validation, but definitely keep that in mind. When you have time ordered data, maybe you just want to do just like split 5, which is just take the last 20% by date and use that as the validation set. Regardless, here we go with k-fold cross validation. We say sklearn.model selection import k-fold. So we have this k-fold utility that we're going to use. This is going to give us all these splits to try out. And how do we use it? Well, we use it like this. We create the k-fold object. We pass in the number of splits, and then we can say k-fold.split and give it the data that we want to split. In this case, we want to split the training input. And remember, the training input is a data frame. So what this will give you is indexes of rows for the training set and indexes of rows for the validation set for each split. So as you call it in a for loop, it will give you 5 splits. So each time you will get a list of indexes of training rows, a list of indexes of validation rows. So we can then take X and from it extract out the training indexes. So let's say it gives us these indexes 0, 1, 2, 3, 4, etc., etc. 20% of them will fall into val IDXs and 80% of them will fall into train IDXs. So we grab those rows from the training, from the input X, and that gives us the X train. And then we grab those rows, and we're using iloc here to grab those specific rows given the indexes. And that gives us the training targets so we grab them from targets, and that gives us training targets. Similarly, the validation IDXs, this contains all the rows, the row indexes for the validation set. We grab those rows from the data frame to give us xval, and we grab those rows from the targets to get val targets. Okay, so now we have xtrain, train targets, xval, val targets. Now we need to actually train and evaluate the model. So I've written a simple function here, train and evaluate, which takes the xtrain, takes the train targets, xval, val targets. It takes a bunch of parameters, like we are passing max depth 4, num estimate is 4, 20, etc. And this is defined here. So with those parameters, which you can see are captured, like a variable number of parameters are typically captured using star params. And then those params are passed directly into a XGBoost regressor. So this is just some Python syntax you can look up. This is called kwargs or keyword arguments. But yeah, we take all those parameters that were passed in, we create an XGBoost regressor. So for each split, we are creating a new model. And then we fit that model to the split data to whatever is there in the current fold. So then the first iteration, we are going to use this as training, this is validation, and create our first model. Then we we make predictions on the train set. So we make predictions on this data, the training set. We calculate the loss. We make predictions on this set, this validation set. We compute the loss. So this was used for training and this was used just for evaluation. So we compute the training loss and the validation loss, RMSE, root mean squared error. And we return all three. We return the model, we return the training loss and the validation loss. And we capture that model, training and validation loss, and we are just printing out the training and validation loss for each split. And we are going to then append the model. We are going to just append the model to a list of models. So because we are training 5 models, we are going to need all of those 5 models to make predictions later. But that's the whole idea here. You split the data 5 ways and then you use a different 20% portion each time for validation. Then you train the model for each of those, you train a separate model for each of those splits. And you can see here, for the first split, the train RMSE was 2352 and the val RMSE was 2424. The second split, the train RMSE was 2406, val RMSE was 2451 and so on. Okay. So this way, when you have a really small data set, especially like maybe a few hundred rows, you may want to just use cross validation and then average the results from all the models. So here is a function I'm defining called predict average. It takes the list of models. It takes a bunch of inputs. It is going to call model.predict inputs for each of the models, and then it is going to take the average. Okay, that's exactly what's happening here. We say for model in models. So we get each model one by one. And we call model.predict inputs. So we give the inputs to that specific each model, get the predictions, and then we take the averages of all the predictions along axis 0. So here's what that looks like. This is the average prediction obtained on the training data by taking the averages of the predictions of all the models. Okay, and you can do that. If you want, you can now break that down. You can say model 0 dot predict X, and you can say model plus model 1 dot predict X plus model 2 dot predict X and so on. And when you want to average them, you can simply just divide by the number of models you have. And that's basically what we're doing with. Yeah, so that's basically what we're doing with that's models. So that's basically what we're doing with predict average. Okay. So that's k-fold cross validation. You use the k-fold class to create some splits, and you can also do randomization. Let's say you want to first shuffle the rows before creating a split. Then you can also specify shuffle equals true. Might be worth a try. You can just do shuffle equals true here. And then you put it in a for loop. You get the train indexes, val indexes for each split. You get the actual data for each split, the training and validation. You train a model, you evaluate the model. You can view the actual results here, and then you can also keep track of all the models and then use all those models together to make predictions. Definitely a more advanced technique, not something that you will have to use for data sets that are large enough, but still a good thing to know. Okay. All right. So that's how we perform k-fold cross validation. Next, let's talk about hyperparameter tuning and regularization. But let's see, maybe you have a few questions here. Okay, I think we've covered these. Yeah, so let's talk about hyperparameter tuning and regularization. Now, just like any other machine learning model, there are several hyperparameters that we can adjust to change the capacity of the model and to reduce overfitting. And this is the typical model complexity versus error curve. When your model is very weak, let's say you're just training one decision tree, then obviously you're going to have a very high error. But as you start increasing the capacity of your model, your training error starts to decrease, and it continues to decrease because your model looks at the training data. It has more parameters to learn information about the training data. So that continues to decrease over time. But at some point, your test error will start to increase. And this is where you have to manage the different hyperparameters and adjust them in such a way that you get to the best fit. you get to the minimum possible test error, and any further you go, the test error should start to increase. So that should be your goal with all the different hyperparameters that you train. Okay. And XGBoost has quite a few hyperparameters. You can check out the documentation here, and there's a detailed explanation about each of the hyperparameters. So once you have that intuitive picture in place, average followed by a decision tree to correct the residuals, followed by another decision tree to correct the residuals, and how we make predictions is simply adding up all the predictions, but with a learning rate applied. Then you can check out all of these different parameters here. This is the learning rate. This is called the min split loss, max depth, min child, etc., etc. Okay, everything to do with trees. So you could experiment with the hyperparameters with k-fold cross validation, which means that every different hyperparameter you try, you could perform k-fold cross validation for it and look at the result. And here is a helper function to help you do that. But because we don't have that kind of time, we want to do quick experiments. So we will just fix a validation set for our hyperparameter tuning. And this is a choice that you will have to make from time to time. So I'm just going to fix a random 10% split of the data as the validation set. So here I'm importing train test split, and then I'm calling train test split with the inputs, with the targets, and setting the test size to 0.1. So that should give me a training set with 90% of the data and a validation set with 10% of the data. And I guess for 1,000,000 rows, 100,000 rows is enough to accurately verify the model. And ideally, again, what I should be doing is maybe picking something from the very end so that the validation set is closer to the test set. But that's okay. Right now, I'm just going to go with a random selection and see what happens. Maybe I'll come back and replace this with actually selecting the last few months of data. But now we have a fixed training set, we have a fixed validation set, and then we have this test params function. So you just give it some parameters and it is going to create a regressor, and then it is going to fit it through the training data. It is going to calculate the training loss, validation loss, and it's going to print it out. That's all. So now let's test different number of estimators. N estimators is the first hyperparameter, probably the most important one. How many decision trees are you going to train? The more you train, the lower the loss will get. So here right now we are looking at 10 estimators, and with 10 estimators we get to, just with 10 decision trees, we get to 2334 validation loss. And you can see that the model isn't quite overfitted yet, because you can see that the train RMSE is 2340, whereas the validation RMSE is 2334. So it's actually lower, the validation loss. Here again, we go to 30 estimators and things have started to get better. We are now only off by $1,000 or $1,800. Again, not bad at all, considering the values that we're trying to predict are in the range of $5,000 to $10,000. So this is not bad at all. I believe this is going to take some time. So maybe we'll let this one run and we will just cancel this execution. But you will see this kind of a trend here. At some point, you will see the best fit, and then training error will continue to decrease, but the test error will start to increase potentially. So as an exercise, do experiment with different values of N estimators and then plot a graph. Try and plot this kind of a graph of the training loss and the validation loss for the different strategies that you've tried. Yeah, for the different strategies that you've tried, and see where you get the best fit. And it's not just about the best fit. Sometimes it's also about what is the additional benefit that you're getting. Let's say by moving to 100 to 240 estimators, the validation RMSE reduces from 1209 to 1190. That's not a big increase, and the amount of time it takes to train 240 estimators is more than double the amount of time it takes to train 100 estimators. So that's where you will have to decide, is it worth the time to add the additional estimators now? If it's not, then maybe you stop at 100, 150, wherever you see that the change in validation RMSE has started to flatten out. So you can stop somewhere here as well. That's not a problem. In a lot of cases, it's not like it starts to increase immediately, but it starts to continue to decrease very slightly for a very long time. And at this point, it just doesn't make sense, because you're creating this huge model, which is only slightly better than this much smaller model, right? So start out small, increase the capacity of your model, And whenever stops making sense to just increase the capacity further, either in terms of the time or because of overfitting, you can stop. Now, similarly, here we have max depth. So as you increase the maximum depth of each tree, the capacity of the tree increases and it can capture more information. Let me maybe stop this right now so that let me do this with a smaller number of estimators so that we can see the effect. Let's say estimators 10. Yeah. So max depth is simply the depth of each tree, the trees that we create to correct the residuals. What is the maximum depth you want to allow them to have? And you can see as we increase the max depth, initially the loss definitely goes down. Once again, experiment with different values of max depth. Now we can see that these are not overfitting just yet. We can see that these models are not overfitting right now. So you can probably still push the model. You can probably still keep increasing the max depth till the point that you start to see some overfitting happening, which means the training error continues to decrease, but the test error actually starts to increase. So the kind of trend that you'll notice is, let's say around max depth of 15, the test error flattens out, and then maybe around max depth of 18, the training error is still going down, but the test error has started to increase. And at max depth of 20, the test error actually starts to, or the validation error actually starts to go up by a significant amount, right? So whenever you notice this trend, maybe you come back and find the lowest point. And also, just to clarify, overfitting is not a situation where the training error has to be 0. That's not the case. Overfitting specifically is described by this scenario where the training error is decreasing as you increase the model complexity, but at the same time the test error is increasing. So the model is getting worse even though it is getting better at the training data. Okay, next up we have the learning rate. The learning rate is the alpha that is applied to the predictions. So this is the alpha. Remember, we take the initial average, then we apply an alpha to and this factor to scale the prediction of the decision tree, and then we apply that to all further decision trees. So we set the learning rate to 0.01. That means it's going to give very less weightage to this prediction. It's going to hardly correct the residual, maybe by 1%. So that makes it very hard for the model to even get good at the training set. So you will need a large number of estimators. So a very low learning rate, something like 0.1, will lead to underfitting, and a very high learning rate like 0.99 may lead to overfitting. It's not that it will, but it may lead to overfitting because you have other hyperparameters as well, right? So one hyperparameter alone cannot cause overfitting, but because there may be other regularizing parameters, but this is the direction roughly that it looks like. Low learning rate, low power, because you're really not giving your decision trees that much weight in their predictions. You're giving a much higher weight to the initial prediction. High learning rate, you're giving the decision trees a lot of power, so it's likely that they may start overfitting through the training set while the test set starts to get worse, or the test error or validation error starts to get worse. So you can see here, when the learning rate is 0.01, the validation RMSE is $5,000. That's way off. That's like we are trying to predict values in the range 5,000 to 10,000. And if you're off by 5,000, that's pretty bad. And hopefully if we get somewhere here, it'll start to get better. I don't think it's going to overfit just yet because we are just at 50 estimators. But let's say we had 500 estimators or 1,000 estimators, and we had given them each a max depth of maybe 10 or something, then you would definitely see that maybe beyond 0.7 or so, the models would start to overfit. But right now it's just because the number of estimators is so low that there's not enough power. Even if you set the learning rate to 1, it may not overfit. There is a question, can hyperparameter optimization be done while combining multiple hyperparameters? Yes, absolutely. It's like if I've put in n estimators 50 here, I could put in n estimators 20, and I could put in max depth of 10, and I could put in whatever I want here, right? So ultimately what test params is doing is creating a random forest, and that random forest is then going to be trained on the data, and then we are going to evaluate it using by making predictions on the training and validation sets, computing the RMSE. So you can modify multiple hyperparameters at a time, but it's generally a good strategy to start with the most effective, or the hyperparameter that is going to have the biggest effect. Let's say the number of estimators, I would think that initially would have the highest effect, and find a good value for the number of estimators. Like I would probably try multiples of 2. I would go 50, 100, 200, 400. And at some point I would start to realize that maybe the benefit is not there of doubling again, or maybe it has started to overfit. So maybe I'll just again maybe find something between 200 and 400 that works best. Maybe try and plot a graph and figure out. So pick the biggest, most impactful hyperparameter first, try and optimize that, then pick the next most impactful one. And how do you figure out which is the most impactful one? Well, typically if you just try 2 values of each hyperparameter, like very quickly, you can see how much effect each hyperparameter has initially. So if the number of estimators is very low, like 10, then changing the learning rate by a lot is not going to cause overfitting very quickly. So yeah, it's a question of just, I mean, it is subjective, depends on the data set, but it's a question of just experimenting a little bit, doing some quick experiments, figuring out which hyperparameters you should optimize first. For gradient boosting, that is typically number of estimators, max depth, learning rate. And by the time we get to learning rate 0.99, RMSE is looking pretty good. But as I said, you can try putting in 500 here and it'll take 10 times longer. But that will tell you if learning rate of 0.99 is always a good idea, especially at a high number of, at a very high number of models. And I'm just going to run all of these cells so that we don't have to wait a long time. Okay. Next up, we have this argument called booster. Now I said that gradient boosting machines use decision trees, but instead of using decision trees, XGBoost can also train linear models for each iteration. So the idea is the same. The idea is pretty much the same, that you initially guess the average as your prediction P0, and then you compute the residual. Then instead of training a decision tree to compute the residual, maybe you train a linear regression model. So maybe you train a linear regression model that tries to fit the data, and then you compute the residuals from the linear regression model, right? And then you train another linear regression model to do it, and then you train another linear regression model to correct the residuals, and so on. So everything remains the same. We just switch out the decision tree classifier, the decision tree regressor internally for the linear regression model. And even all of these things like the alpha and everything remains the same. So all of the hyperparameters can remain the same. And if you think that there are more linear relationships within the data, then you can just test out linear relationships as well. And it seems pretty fine to me, not too bad. 2727 is the output here, the validation RMSE. So that's not bad at all. So maybe you can try experimenting with some other hyperparameters, experiment with the linear and the tree-based model, and figure out which one works best. Now, what will happen over time is as you train dozens of models or maybe hundreds of models, you will start to get a feel for how all of these hyperparameters interact with each other and which kind of hyperparameters are better suited for which kind of data. A lot of this is fairly subtle in the sense that it is not something that is documented explicitly. It is not something that a lot of people are even able to express themselves. Express clearly in words, but it is something that they know, something that they understand. It's kind of like a muscle. So the best way to become good at machine learning is to just train a lot of models, like every day, just be training some model on some data set. And a great way to orient yourself when training models is by participating in a Kaggle competition, where you can just train a bunch of models and make a submission and see if your model worked better or not. And trying to stay organized using spreadsheets or whatever tools you need to use to stay organized, where you note down all your ideas, all your experiments and their results. And you just keep doing that over and over. And whenever you're stuck, you look for help. And the places you look for help are typically Kaggle forums, where you look at the discussions, or maybe you look at some tutorials online, maybe you look at some videos online and apply the techniques that you read there. And sometimes, like when you get to a point where you've applied a lot of these techniques and none of them work, you may have to start reading papers. So sometimes you may end up doing that. And that's how you get good at machine learning, right? So there's definitely more theory that you should learn about machine learning eventually over time that will be useful, but understanding the theory will not help you beyond a point. Machine learning is an applied science, an applied field. So the more models you train, the more experiments you do, the better you will get at it. Okay. And a great way to learn is also by looking at what others are doing. All right. So here's an exercise for you. Try and experiment with all the different hyperparameters. And there are several other hyperparameters, as I've said earlier. These are not the only ones. Gamma is another one. I think gamma indicates what is the minimum reduction in loss that is required to create a split. Then you have min child weight, which indicates, which I think indicates what percentage of rows each child should contain or something like that. Then you have max delta step. What should be you'll have to check this out. I'm not sure about max delta step. Then you have subsample. For each tree, instead of using all the rows, you can also just use a fraction of the rows. So that's subsample. You have call sample by tree, which means for each tree that you create, instead of using all the columns, you can simply use a fraction of the columns. Instead of using all 120 columns that we have right now, maybe you just use 100 columns each time, randomly chosen. And that again creates some kind of randomization, right? Yeah, so those are some of the things that you can try out. And let's train a final model on the entire training set. And this is also common practice that you will have a validation set, or maybe you will do cross validation, and you will try many different kinds of experiments, and then you will arrive at certain hyperparameters. Now, once you've arrived at a certain set of hyperparameters, which you know or you believe are the best, at the very end, one last time, you can train your model on the entire training set, which means including the validation set, because now we are done evaluating. Now we are done evaluating different types of models and different hyperparameters, and we've decided that these are the hyperparameters that work well for this data set. So at this point, it just makes sense to maybe just train with the entire data set, get a little final boost, because more data is always helpful for the model, and then make predictions on the test set and then submit that to Kaggle. Okay. So always do that. Have a validation set, use it till the very end. But when you're making predictions, just train the model with the entire set. Okay, so this may take some time. I think I've set the number of estimators to 1,000. I believe it took about 8 seconds when we had 50 estimators. So it would take 5 minutes or so to run this. Okay, so now we're training one final model on the entire training set with custom hyperparameters. These are the hyperparameters we've chosen. 1,000 estimators, a learning rate of 0.2, a max depth of 10, a subsample of 0.9, which means each decision tree only uses 90% of the rows randomly chosen, and a column sample by tree of 0.7, which means that each decision tree only uses 70% of the columns. And then we fit the model, and it took about 5 minutes on my computer. And this is still running on Colab, so maybe it'll take twice as long. And this is the model that got created. Then we can evaluate the model as well. So we can create training predictions. Model.predict X, and then we can do a RMSE on the train preds and train targets. Okay, there seems to be some issue here, but yeah, ultimately you can evaluate the model using the training set. And of course, that will not be the true reflection of the performance of the model. It's just that we don't have a validation set right now because this is the final training we're doing. But we train the model, and once the model is trained, we can make predictions on the test set. So remember, we have the test set as well. If I just check X test, So this is X test. It contains all the information in exactly the same format as the training inputs X train. So we can pass X test into model.predict, and that will give us a bunch of predictions for the test set. Let's check test preds. So here is all the predictions that we've generated for the test set. And of course, test preds applies to these IDs. So we know that for ID 1, for the first row of the test set, the prediction is 4207. For the second row of the test set, the prediction is 7587. For the third row of the test set, the prediction is 8849, and so on. And we have to create the submission file. So we already have the submission DF. Here we have IDs and then these random sales. Actually, let me just load that up again. So pd.read CSV, Rossmann store sales / submission.csv. So we are given this sample submission file. Yeah, so we're given the sample submission file, submission.csv, and the sample file contains IDs 1241088, and it contains the value 0 for sales. Now we have to fill in, instead of the value 0, we have to fill in our predictions. So these are our predictions, test preds, and we can do that here. So we just say submission df sales equals test preds. And once we do that, we can now see we have submission df. So here we have the IDs from the sample submission file that was given to us. And instead of having 0 sales for everything, which was the sample submission, we have replaced those zeros with the predictions of our model, 4207.07 and so on. And we know that these predictions line up with the IDs because these predictions were generated using the test set, X test, and X test came from test DF, and in test DF these IDs were in the numerical order. Okay, so especially with Kaggle, you need to be careful. Make sure that you're not shuffling your test set so that the predictions that you make on the test set line up with the original IDs or whatever identifier is there in the submission file. Okay, so now we've created this submission file, the submission data frame. Now there's just one thing we have to handle here. Recall that if the store is not open, then the sales must be 0. And this is not something that we are accounting for in our model. Our model simply assumes that the store is open. So we need to hard code this rule that whenever the value of open in the test set is 0, then we can set the sales to 0. Okay, so in some cases here, maybe we have to check if that particular row had store open set to 0. And if it did, we simply set that to 0. So here's one way you can do that. If you just check test df, in test df you have ID and you have some information and you have store, and store open is either 1 or store open is 0. If store open is 1, then we can simply keep our prediction, whatever prediction we have made. If store.open, if the value of the open column is 0, then we should simply set that value to 0. So here's a trick that I can apply. If I simply take the sales column of the submission and multiply it with the open column of the test data frame, which is also lined up by IDs. So wherever the store is open, the value will remain, and wherever the store is closed, the value will turn into 0. So that's what I'm doing here. I'm just going to do submission df sales multiplied by test df open. Okay. So the ones will retain the values, but the zeros will convert the values to 0. And that is what we want. When the store is closed, the sale should be 0. Now there is one minor issue here. In some cases, the value of open in the test data frame is nan. So this is where again, we'll have to figure out why is this data missing. On those dates, were these stores open or closed? But for now, I'm just going to assume that wherever the data is nan, I'm just going to assume that the store was open. Maybe not the best assumption, but let me just assume that wherever the data for open is nan, the store is open. So I'm just going to fill NA with 1. And now we have the submission data frame, and it is going to have a bunch of zeros as well. And you can see it if I just check the sample, let me see, sample 20, you will see that you have zeros in certain places. And these zeros have come by multiplying the value of open. Okay, I think we have been able to train the model here as well. So let me just return to Colab here. So we make predictions on the test set, and then we put these predictions into the submission data frame. And then we have the submission data frame that we've created. Okay. All right. So we just did all of that stuff locally, but the same thing we just repeated on Colab as well. So now we have submissions from our model ready to be added, ready to be submitted to Kaggle. So now we can just save this file submission.df.tocsv as submission.csv, and we set index to none. Here you have submission.csv, and I'm just going to download this file. And that's downloaded to my desktop, submission.csv. And then I'm going to go on the competition page here. And on this competition page, I'm just going to click late submission because this competition has ended, but I can still submit and see a score and upload the submission.csv file. So it's going to take a minute or so to upload. And you can also describe your submission because you can see your past submissions and it'll be easy to just check things out. So let's see. Maybe this is what I'll do. I will simply copy over this. I think this is a great way to describe my submission because it has all the hyperparameters. Yep. I think you can even write it as code. So maybe let me just do this. Yep. So this is the information. This is everything I need to know about my submission. And I click make submission. And that gives me a score 0.13152. Let's see where that lies on the leaderboard. 0.13152. 0.13152. Well, it's already pretty bad, but actually, yeah, it may be good enough because there are 3,200 participants and 0.13. Okay. Looks like it's a long way down. Yeah, somewhere here. So we are in the top 50%. And that's not bad. If you're in the top 50% of a Kaggle competition, then you have a decent model and you will see that the gains are actually pretty small beyond that point. Like from 0.13 to 0.11, the overall gain is of about 10%, right? So you have achieved about a 90% possible reduction in the error. And mostly here, in a lot of cases, the top submissions often have a lot of models, maybe they ensemble like 10 models, and we've not trained a very big model, even though it took about 15 minutes. We've only put in 1,000 estimators and a max depth of 10 and a learning rate of 0.2. People do a lot more. You can imagine setting a model to train overnight with maybe 10,000 estimators and a different learning rate and a different max depth. Of course, you have to first do some experiments to figure out that you're not overfitting. But often, especially with gradient boosting, these models can run into hours, the training times, and you can use GPUs. So one thing that I would encourage you to check out is how to train an XGBoost model on a GPU. And you will see a significant speed up if you use a GPU, sometimes even 10 to 100 times faster. And GPUs or graphic processing units are very efficient at performing matrix computations, which is the kind of computations that XGBoost requires. Okay. And now here we have not done cross validation. So one thing we could do is we could also do k-fold cross validation. That would give us 5 models, and then we could average out the results of those 5 models. Or another thing that you could do is you could train 5 models with 5 different sets of hyperparameters, and then average the results of those models. Yet another thing you could do is you could train the best possible random forest model, the best possible gradient boosting model, the best possible deep learning model, the best possible SVM, support vector machine kind of model, and then average all of their results. And one other thing you can do there is, instead of just blindly averaging all their results, maybe apply weights to the results of each of the models. Give each model a certain weight and optimize the weights. Now, one way you can optimize the weights is by hand tuning each weight. But the other way you can do that is you can do something called stacking, which is train a linear regression model on top of those weights to figure out the best weights to apply to each model, right? How much weightage should be given to the XGBoost regressor? How much weightage should be given to the random forest, etc., etc. And those are all the techniques that people apply to get to the top. Like the first 100 or 200 submissions would all have several models. As you can see here, there you can even form teams on Kaggle. So on Kaggle, you'll find that these 5 people would each have trained maybe 5 models, and they would each have worked independently, trained 5 models, and then the team would essentially mean ensembling the results of each of those 5 models by each of those 5 people. So you give your results, and this person gives their results, and this person gives their results, and so on. And then they average the results and they simply submit that. And that itself gives them a huge boost, because the more different kinds of models, the more different kinds of ideas that you combine, the more the effects of ensembling work, or the wisdom of crowd kicks in, or the errors cancel out. Okay. So that's making a Kaggle submission. I encourage you to try out different hyperparameters and beat the score. Should not be too difficult. Take inspiration from the top notebooks in the code tab of the competition. And here is another exercise for you. Just save the model and all the required objects using joblib. We did this for decision trees. The process is exactly the same, where you create a dictionary with all the important useful things that you need to do to take any input and make predictions on the input, and then save that dictionary using joblib. Yet another exercise for you is to write a function predict input. So predict input should take a dictionary, and in that dictionary we can put in all the columns of data that are there in the training data set. For example, a date. Let's see what that looked like. So let me just see ROS TF. Yeah. So here is a sample input. Let's say I give you a sample input. In the sample input, store is 2, and then day of week is 4, and then date is something else, like let's say one of these. And then you have, of course, you won't have sales or customers. You will only have open. So let's say open is 1. And then you have promo and state holiday and school holiday, etc. Okay. So given an input like this, can you write a function to make a prediction from the model? What are all the things that you will have to do? Well, first thing you will have to do is put this input into a data frame. So let me just do pd dot data frame. And here I'm just going to give it a list of dictionaries, and just one dictionary here. So sample input, and let's call this input df. Yep, there we go. Input df. And then you would then have to perform all the pre-processing that we had performed earlier. Of course, I should also put in this information. Let me just add that quickly. State holiday is 0 and school holiday 0. Yeah, so that's your input data frame. The next thing you would have to do is you would have to merge with stores df. So that would look something like this input df dot merge store df on store. And let's just put that in input merged df. So that's what that will look like. Next, you would have to do all the feature engineering. So that you have done, which is the dates, the competition related stuff, and then the promo 2 related columns. You have to add all those columns here. Next, you will have to do some pre-processing. So for the pre-processing, you would have to fill missing values or imputation, and then you would have to do scaling using the same imputer that we had created in the same scaler, and then you would have to do the encoding for the categorical data. Then you can pass it into the model. Of course, only after selecting the right set of rows. Selecting the right set of columns, which is just the numerical plus encoded columns. Okay. It's always good to just write this out, and then it becomes a lot easier to actually do it. So now for feature engineering, let's do the dates. So what was that function called? I don't recall, but let's say, was it date something? Let's look it up here. Yeah, split date. So let's call split date now on the data frame. So split date on input df. Then let's add the competition related data. So here we have comp months on input df. Then let's add the promo check. So promo calls is what it's called. Promo calls input df. And let's look at input df after this, or this is called input merge df actually. Input merge df here, input merge df here, input merge df here. Okay, this should be, I think this shouldn't be 31. This should be 30. This is not a valid date. So let's just get that fixed. Yep. So now we have input merge df. Now we have input merge df. Now we have all these rows. Now we need to perform the imputation. Well, there's no imputation to be done because there is a competition distance already. So this is not required. There is a scaling required. So I'm just going to do input merged df numeric calls equals scalar dot transform, and scalar already has the scaling parameters, input merge df numeric calls. And then there is also an encoding required. So input merged df encoded calls. So remember the encoded columns, we have already saved the names, and we say encoder dot transform input merged df categorical calls. Okay, so that is the imputation and the scaling. Okay, I think I may have to just do it a little more carefully. But once you do the imputation and scaling, then you can maybe just select the numerical and encoded columns. And once you select the numerical and encoded columns, then you should be able to make predictions on the dataset. Okay. I believe I forgot to add promo. Let me just add that here. Yeah, let me just add the promo here. Yeah, I just missed one factor in the input. And there seem to be some other issues there as well. In any case, we will fix all of these, and once you have that, you will get an X input, and the X input will simply be input merged df numeric calls plus encoded calls. These are the one-hot encoded columns, and then you can pass it into the model. So you can say model.predict, and you can give it X input, and that will give you a list of predictions. Of course, there's only one element in the list, so you can just select out the 0th element, and that should give you the prediction. Let's maybe take just a small second to fix this. Isnan is not supported for input types. The inputs could not be safely coerced. Okay, maybe I've still missed some column somewhere. So I'm just not too sure. Maybe I just have to do this a little more carefully and this should be fine. Test df. So we have the store, we have the day of the week, we have date, open, promo, state holiday, and yeah, I think we have all the information. So I'm not sure what the issue is. I see. Maybe this should be A and this should be 0. Yup. All right. Okay. Now we fix the input and this is the prediction for the input. So the prediction that our model makes is 6026.005. So the model predicts that given this input, sample input, the output or the sale on this particular date is going to be 6026 based on everything that it has learned from our data. Okay. And that's how you use the model. So you have to perform all these pre-processing steps onto this simple input before you can make a prediction. So that's all for today. We learned about gradient boosting, and gradient boosting is a very simple idea where we first predict the average as a prediction and then we find the errors that our prediction has made and we train a decision tree to correct the errors, and then we make new predictions using the initial prediction and the predictions of the decision tree scaled down by a learning rate, and that gives us new errors, and then we try to correct those errors with the second decision tree and so on. So we looked at how to download a real world dataset from a Kaggle competition, and we looked at how to perform feature engineering and prepare a dataset for training. This is a very important part, and this is something that you will have to learn with practice by looking at what other people are doing. We looked at training and interpreting a gradient boosting model using XGBoost. There is also another library called LightGBM, which works exactly the same way, but it has certain optimizations that might be useful for larger datasets, and some of the ways in which it operates, some of the internal implementations are different. Ultimately, both XGBoost and LightGBM are implementations of several papers in the space of tree-based learning algorithms and gradient boosting. So check out what the differences are. Then you also have, we also saw how to perform k-fold cross-validation and how to combine the results of the k-folds. We also learned how to configure a gradient boosting model and how to tune hyperparameters of the model, which is essentially by going up and down and figuring out where we are getting the best fit and going with the most impactful hyperparameter first and then slowly going through all the other parameters. Okay. And that's what machine learning engineers or data scientists and ML practitioners do all day. Create new features, tune hyperparameters, and think of ways to just improve the data for the machine learning model and maybe get the machine learning model to train a bit faster as well. Here are some resources you should check out. There is definitely a lot more about gradient boosting that we've not covered here, but this should serve as a good introduction. Now let's go back to the course homepage and talk about the course project. Let's scroll down to course project, where you will train a real-world machine learning model from scratch. In the course project, you will apply your machine learning skills that you've learned in this course by training an ML model on a real-world dataset. And these are the steps that you will complete to work on your project. First, you will pick a large real-world dataset from Kaggle, and we have a section of recommended datasets to choose from, and you can also choose your own. And you will download it using the Open Datasets library, just as you've done in the previous lessons of this course. Your training set should contain at least 50,000 rows and 5 columns of data. This is important because when you create the model and publish it online, it will be a great project to showcase on your professional portfolio, especially when you're applying for jobs or internships. So once you've picked a dataset, you would then read the dataset description, understand the problem statement, describe the modeling objective clearly. This is very important. Before you start any modeling, you have to understand what the business requirement is. You have to understand what type of problem it is, whether it is a classification problem or a regression problem. And you have to describe the modeling objective, identify which column you're trying to predict, and what inputs you need to use to predict it. You can also browse through existing notebooks created by others for inspiration. Next, you will perform exploratory data analysis, and then you will gather some insights about the data. You will perform some feature engineering. You will create a training validation split, and you will prepare the data for modeling, which means imputing any missing values, scaling numerical values into a small range, and encoding categorical values. Next, you will train and evaluate different machine learning models, and you will tune hyperparameters and reduce overfitting to improve the model. This is the fun part. This is where you'll spend a lot of time testing out different models, different hyperparameters, different experiments. And then you will report the final performance of your best models. You would then want to show some sample predictions using your model and then save the model weights. You can summarize your work, you can share links to any references that you found useful, and you can suggest ideas for future work. Finally, you will publish your Jupyter Notebook to Jovian, and you will make a submission here on this page, and you can share your project with the community. Optionally, you may also write a blog post and contribute to the Jovian official blog. There is no starter notebook for this course project, so you can just use the new button on Jovian to create a new notebook. So click New, Blank Notebook, type the name of your project, and select a privacy, and click Create. Create will just create the project, and then you can run the project on Google Colab, or you can click Create and Run, and this will create the project and directly run it on Binder. All the notebooks that you create are part of your Jovian profile. So if you just go to jovian.ai, and on your Jovian profile, go to the Notebooks tab, you will be able to find the previous notebooks that you've created. So use Jovian to keep track of your notebooks, to version your notebooks, and also to share your work. Now let's review the evaluation criteria and some recommended datasets for your project. So your submission should satisfy these criteria. The training set should contain at least 50,000 rows of data and 5 columns. Your notebook must include all the steps listed in the project guidelines above. Your notebook must be executed end-to-end with error-free outputs for all cells. And your notebook must train at least 2 different types of machine learning models. You don't have to stop at 2, but you need to do at least 2. And you must tune at least 2 different hyperparameters for your chosen models. Now your model's performance on the validation set should be reasonably good. This means that it should not be too bad, it should not be worse than a random baseline model. As long as your model is reasonably better than a random guess or maybe a fixed prediction, that's a good model. And your project must be documented extensively using Markdown cells. Documentation and presentation is a very important part of machine learning, so please make sure to include that. Your notebook must include references to relevant notebooks, tutorials, and documentation sites. And your notebook must not be plagiarized, that is directly copied from another project. So please keep this in mind as you work on your project, and you need to meet all these criteria to get a pass grade. Now you can use Kaggle to find some real-world datasets, and you can also look at past Kaggle competitions for inspiration. Here are some projects that we have curated for you to choose from. You can go through this list of projects. There are about 60 different topics, and don't worry if somebody else is working on the same dataset, because you can always try a different kind of model, and the approach that you follow, the analysis that you perform, the features that you create will make your project unique. The important thing, irrespective of which of these datasets you select, is to do good original work. So let's go through one of these project ideas. So here let's look at home credit default risk prediction. So let's open up this dataset. This is part of a Kaggle competition that ended 3 years ago. And the first thing you would want to do is read through this description. So it appears that this dataset contains some information about home credit or about loans, and you want to predict how capable people are of repaying a loan. So that's the basic idea. I encourage you to read through all the different tabs here in the overview. It's also very important to look at the evaluation criteria for your project and use that to evaluate your models if possible. But let's move on to the data tab. You can see that you have a bunch of different files here, And it appears that there are two main files, application train.csv and application test.csv. And then there is a lot of other data that you can use to augment the training and test data. So keep that in mind. You don't have to use all the data, but in a lot of data sets, you will find a lot of additional data that you can augment your training data with. And let's come down here to application train.csv. It appears that we have 122 columns, and the second column, target, seems to be the column that we need to predict. And you can verify this by opening application test.csv. And application test.csv does not have target and has only 121 columns. Now coming back to application train, if you check the column tab, here you will be able to see how many values you have for each column. And you can see that there are over 300,000 rows of data. So this meets our evaluation criteria. We need the dataset to have at least 50,000 rows and 5 columns. In this case, we have 300,000 rows and 122 columns. So that's great. Now, if you wish, you need not use all 122 columns of this dataset. If you wish, you can just use maybe 5 or 10 columns. And if you wish, you can just use 50,000 rows of data to meet the evaluation criteria. But we encourage you to use as much of the data as you can. So you will need to download this data. And to download this data, you can use the Open Datasets library. The Open Datasets library can be used to download data from a Kaggle competition, just like this. You say import Open Datasets as OD, give it a dataset URL and call od.download. And that will ask you for your Kaggle credentials, and you can put in your Kaggle credentials to download the data. This is also something that we've covered in previous tutorials. So I encourage you to check out the previous lessons to learn how to download this data on Kaggle. And once you download the data, then you would follow the steps mentioned here. The next step is to identify the modeling objective. In this case, of course, the modeling objective is to predict the target column, and the target is 0 or 1. So this is a classification problem, not a regression problem. So you can apply techniques like logistic regression, decision trees, gradient boosting, but make sure that you're using classifiers and not regressors. Next, you will perform some exploratory data analysis to gather insights about the data, perform some feature engineering, create a training test validation split, and prepare the data for modeling. Now, you can do a bit of exploratory analysis yourself, but you can also use the code tab, and on the code tab, look for some of the most popular notebooks. If you sort by most votes, you should be able to find a bunch of different notebooks here on the same data set. And feel free to go through these for inspiration. Now, you can use some helper functions from some of these notebooks. You can use a little bit of code from here and there, but definitely do not plagiarize any notebook. The idea is for you to learn. That is the most important thing. And you should be able to draw the line where you are using a specific part of some notebook to make your work easier versus taking code and not learning from it and not understanding it. So to get the most out of this project, make sure that every line of code that you read or every line of code that you use from somewhere else, you understand what it does and you use it to apply your own original ideas. So please keep that in mind. Then once you perform exploratory data analysis, you will then train and evaluate different machine learning models. Once again, for inspiration, you can see the kinds of models people are training here. LightGBM seems to be a popular choice. So just search for a specific term here. If you're looking for XGBoost, for example, you can search for XGBoost and you can find a notebook for XGBoost. And then you can train and evaluate different machine learning models. You can tune the hyperparameters, reduce overfitting, and improve the model. Finally, you can report the performance of your best models, show some sample predictions, and save the model weights. Then summarize your work, share links and references, and suggest ideas for future work. And finally, just publish your Jupyter Notebook to Jovian and make a submission here by pasting your Jovian Notebook URL. Please make sure to run jovian.commit from time to time to record different versions of your notebook. And again, make sure to review the evaluation criteria and the recommended datasets. There are quite a few datasets here for you to choose from a variety of different domains. And you don't have to use one of these datasets. You can also select a dataset from any online source of your choice. So this is going to be an exciting project and you will apply everything that you have learned so far and you will learn a lot more in the process. And do share whatever you're doing with the community. Do feel free to ask for help. Once again, I would encourage you to check out our Discord server if you haven't already. So just click on the Discord link and you will be able to join the Discord server. In the Discord server, we are having hundreds of interesting discussions. So what do you do next? Review the lecture videos and execute the Jupyter Notebook. Complete the lecture exercises and start working on the project and the assignments, and discuss on the forum, ask questions, share references, and help others. So with that, I'll see you in the forums, and you can find us on 0togbms.com. You can also connect with us on Twitter at @JovianML and @AkashNS. Next week, we will look at unsupervised learning and recommendations, which is our final topic in machine learning with Python 0 to GBMs. Thank you and have a good day or good night.